Okay, so I hope you had a lovely flight.
Do you want us to take a test or not?
Yeah, test. Pause this real quick. Yeah, that was my first thing I wanted to talk. This is a wonderful, wonderful, wonderful place. Oh,
Skirt.
gosh. Why did somebody just take this and put it on the desk next to them instead of passing it to the next person? That was the last class. They didn't pass the paper. But that said, it's a good reminder for me to give you your papers back. Here are some homeworks. There are three, and then probably a little bit of makeup type work that you might not have any paper in. There's one, two, three. Okay, sorry about that. Now I'm really ready to teach. Here we go. So it's two really different ideas, tangent line and higher order derivatives. Tangent line, students tend to do pretty well with this. Having taught this class a few times, I'm aware of a few common mistakes, and we're going to make sure you don't make those mistakes, and you'll be able to do this well by the end of this lesson. So let's start here. Say I wanted to estimate something in the square root. Now I'll come to that later. The first thing before you can use the tangent line, you actually have to be able to find the tangent. So let's start there. If I wanted the equation of the tangent line to this function at the square root of 4, or at 4, then I really want to find what's the equation of that. That's what I'm trying to find. All right? We will typically do this in a three-step process. Point, slope, then point, slope. Identify a point on the curve. Now, sometimes they're going to say, find the tangent line at blank. And in which case, the identifying part is pretty easy. You already know that the x is 4 that I'm going to square root. And all you have to do then is say, when I put 4 into the square root, I get 2. The point I'm drawing the tangent line at is 4, 2. Now that's a common point. It's on both the curve and the tangent line. All right. Now to find the slope, we know that the slope of the tangent is found by taking the ... You speak calculus? Derivative, yay. Please do this in 2 steps. This is one of those common errors. People bleed one step into the other and then they lose points for notation. This is particularly happens on people that are good at calculus and feel comfortable and start trying to combine steps. Tell me, given that this function is x to the half, start by taking the derivative at any point x, and then at the point I'm interested in. What is the derivative of x to the half? Yeah, 1/2 x to the negative 1/2, which normally I wouldn't care if that's ugly, but in this case I want to use it for something else, so it might help to clean it up. It is, I think it was Danielle who said that, I'm not sure, but 1/2 root x is the derivative cleaned up. You follow? You with me? Now, particularly at 4, I don't want the derivative at any old point. I want the derivative, what is the slope at 4? Well, that means f prime at 4 instead of at x. Using good notation, telling the person, now I'm finding the derivative at 4. This is different than the derivative at all x's. Now I'm at the derivative at 4. And that is 1/2 root 4, which is 4. Does that seem to look right with my picture, that the slope would be 1/4? Seems logical, yeah, it's flat, it's positive, so it seems reasonable. Now the tangent line equation. Tangent line equation is usually done in point slope form. It's not because, math teachers like to get crazy with you and leave your slope intercept form. You're going to always have a point and a slope. It's just logical to use point slope form. So using point slope form, if you're not good at point slope form, you best get good at it because you're going to do it a lot. The idea is that given a point, x1, y1, and the slope, which is the derivative, you write the line. So what's y minus y1 going to become? Y minus 2. That y1 is the point, the y part of the point we're passing through. The slope is 1/4. That's from our derivative calculation. And x minus the x of the point is. Now, if you needed to, I suppose you could, if necessary, on a multiple choice, you could go to slope-intercept. Let me make this very clear. On the homework, I don't care if you leave it in point slope. In fact, I prefer you leave it in point slope form. Don't waste your time, all right? I don't care if the answer in the back of the book is slope intercept. I don't care. Leave it in point slope form, and you're good. You sometimes, though, do need to change it, multiple choice style. So if you wrote this in slope-intercept form, wouldn't you move the 2 over, distribute the 1/4, combine like terms, and you might get something like 1/4 x plus 1. Does that look right for that black line that I wrote? Yeah, it's right on. You follow? You try, please. Try the tangent line to cosine at x equal pi over 6. Do not use a calculator at any time. Feel free to tough it over with your Mathemegos, however. Please leave it ugly. It should have pies in it. It should have roots in it. It should be ugly. I bet you test some of you have rock solid trig skills. Some more like squishy jello trig skills, not super rock solid. But we'll get there. Please show, when you go to find the slope, please show me 2 steps. The derivative generally at x, and then the derivative specifically at pi over 6. What's the derivative generally of cosine? Negative sine, okay? The derivative at pi over 6, that is, negative sine of pi over 6, which is negative what? Negative 1/2, yeah? So my tangent line equation, that is y minus root 3 over 2, negative 1/2, x minus pi over 6, okay? The number one most common error on this is this step is sometimes forgotten. People know they need to take the derivative to get the tangent slope. And so they say, okay, so I got the point, I got the derivative, so here's my tangent line. Y minus root 3 over 2, the slope is the derivative, so boom, there's the derivative, x minus pi over 6. Why not that? So what are you trying to find here? We're trying to find the equation of a tangent line. Emphasize line. Is that a line? Yeah, no, that's a freaking mess. Sine is not a line, okay? So if your slope is not a number, you are doing things wrong. This is a line that should have a linear slope, a number. So please don't just, okay, take the derivative and call it good. It's the derivative, then the derivative at that point to see what's the slope at that point specific, right? The fact that it's negative slope makes sense in terms of the graph. My answer seems reasonable. Let's try making sure you can do this with the calculator. Get out your calculator, please. Put it in radian mode or go to your scratch pad in radians or whatever document you have that's in radian. Make sure it's in radian. I should put this back up. We're going to find the equation of the tangent line to e to the sine plus 3 tangent 5x. E to the sine plus 3 tangent 5x. So I would, because I'm going to use that for a couple different things, the point and the slope, the derivative at that, I'm going to put that into my function. Name it e to the sine of x. Oops. Plus 3 tangent 5x. I could look at the graph. That's really nice. That's cool. But I don't really care what the graph looks like. I'm going to go back to your home screen. Now, to find a tangent line, we need a point and a slope. And then we write point slope. So how will I find I have the point. I asked the question is half done as far as the point. I know I want the tangent line at 2.75. That's the x. I need the y. Surely 2.75 is nice. The y. Evaluate the function at 2.75. Let's all see if we agree. Call up your function. 2.75. If you have an 84, it absolutely will do all this too. Please let me know if you are in 84 and you're not sure how to accomplish y1 parentheses 2.75. But it should be, I get 8.822. How about you? You concur? Always give me 3 or more decimals in this class and on the AP test, rounded or truncated. So in this case, they would be the same. But we've got our point. So far, so good. Do you remember how to find the derivative in your calculator? If you have an Inspired, how do you find the derivative? Menu, calculus, numerical derivative. The variable is indeed x in this. I have it as a function of x. The value is 2.75. First derivative doesn't make any sense, but in an hour, or no, 10 minutes it will. Hit OK. You need to then take the derivative of f1 of x. Don't just type in f1. You have to say the derivative of x with respect to x. Wow, I get a really steep slope, which I guess jives with my picture. Did you get 103.867? That's a really steep slope right there. Anybody not get that for their derivative? Okay. So we have, now, in terms of notation, I would say something like this. I don't, as opposed to up here where I said the derivative at any x and the derivative at the point, on the calculator I'm not finding the derivative at any point. The calculator doesn't do that. It won't tell you the derivative of a function. It does, however, calculate an estimate of the slope. It's a numerical estimator. So you can just jump straight to that step. The derivative, the slope, which is the derivative, is approximately equal to, and what was it, 103 something or other, 103.8675. A bit about rounding, truncating. If you truncate to 3, what do you give me? Truncate means to cut. So if you truncate after 3, then you're giving me 103.867, and that's fine. If you round, you would give me 1.868, okay? I don't care which one you give me. You can give me 4 if you like. You can give me 5 if you like. You can give me more. You just can't give me less. I typically report 4 on my work. That's just because as a teacher, I need to know if people rounded or truncated well, so I need to see 4. You'll see in my work often then 4. 103.8675. All right. 103.8675. Again, 867 or 868 would be fine. Your tangent line is y minus 8.822 equals 103.867 or 868 or 8675. X minus 2.7. How did you do that? Questions? Yes?
When I did the slope at 2.75, I got almost 3.842.
What kind of calculator do you work with? Yeah, that's a little inspired, a little more accurate. I think they go to within 100,000. The calculators find slope between 2 points. It doesn't know calculus. The problem is the Inspire takes 2 points very much, quite a bit closer than you did before. You'll be fine. It's only on things that have huge magnitude, like exponential functions, that there's error. I will be aware when I get a grade that there's so, okay. And on the AP test, they would choose something with that high magnitude that would show up. Okay, tangent line to estimate. This is one of the big reasons why you do a tangent line. It's fun. And in physics, tangent lines are often done as well. For example, if you were orbiting the Earth, yeah? And you wanted to escape the Earth's orbit, you would have to reach escape velocity, right? Now, if you went faster and faster and faster until finally at this point you reached escape velocity, then when you go off in a tangent line kind of way. Keep going in that direction that you're going at the instant you reach escape velocity. Tangent lines then are used a lot in physics, but they're also used a lot in math just to estimate. Square root of 5, for example, is the one I want to talk about. Now, if I were teaching this in pre-algebra, I'd say, all right, kids, let's estimate the square root of 5. And I would say, what do you think it's between? And they'd say the square root of 5 I know is between 2 and 3. And I'd say, all right, what should we try first? And they'd say, oh, let's try 2.1. And so when they say try 2.1, you multiply that by itself. And then you multiply this by itself. And it would be between 2 and 3. So you'd have to go there. And after the end of the day, they would get a decent estimate. And it would probably take a about 15 minutes. I'd budget that. You can do this in calculus in 1 minute. Better than those. So let's do this. And thankfully, we already have the tangent line, so this will even go quicker than this. Look at picture-wise. This is so good, it's actually hard to show in a picture. But we know that our tangent line that we found at 4 was this, yeah? All right. Now, consider if I zoomed in. Actually, I'll go here. I want the square root of 5. Now, that would mean if I put 5 into the square root function, what comes out? Obviously, it's a little more than 2. But that would be the perfect square root of 5, yeah? The tangent line is used in such a way that we say, well, gosh, look at where the tangent line is at 5. If I were to say, put 5 into the tangent line and trace it over, gosh, isn't it just barely above? I mean, if I zoom in, here's the tangent line. Here, at 5, they're very close. The y values are very close when x equals 5, yeah? The thought process then is if they're pretty close at 5, then I could just put 5 into the tangent line. Well, why would I do that? Well, isn't a tangent line really easy to work with? I mean, tangent lines are linear. We could easily put 5 into a tangent line because the equation's so clean. So, given our tangent line from the previous work, which was y minus 2 equals 1/4 x minus 4, we could plug 5 into that tangent line instead and see what's the y for the tangent. If I do that, then I would first move the 2 over, I reckon, because the y is going to be 2 plus a little something. That 2 is kind of a baseline value, and then this figures out how much would I expect it to change above 2 or change from 2. So I'm going to then say 2 plus 1/4 of, and in place of the x, I'm going to put in 5. You follow? How does that come up? 2 1/4, or 2.25, yeah? So we're estimating that the square root of 5 would be about 2 1/4, 2.25. Now, this will hit, this I could talk about all day. But just so you have a little bit of an appreciation of what's going on here, the y for the tangent line is the baseline 2 plus how much I expect it to change given the rate of change there. This 1/4, what it means is change in y over change in x. The curve is changing 1 unit of y for every 4 units of x, is what that slope means. But I'm only changing x by 1 unit because I'm going from 4 to 5. So y will only change by 1/4 unit. That's then baseline 2 plus a little bit more change of a 4 puts me at 2 1/4. Do you see what I'm saying? Sure you do. Okay. Without using your calculator, is our estimate above or below the true square root of 5? When you punch in the square root of 5 in a second, will you expect to be less than 2 1/4 or more? Look visually. Think graphically. Less. Why would the estimate be less? The square root of 5 will be less than 2 1/4. Why? Graphically. Yeah, because the tangent line, because the curve, which is the actual square root of 5, is below the tangent line. And so the y for 5, the square root of 5, will be a little less than the minus value of 5. So I would expect an overestimate. Would you please tell me what is the error? How would I calculate the error of my estimate? Now, visually, that's the gap between the two. The true curve at 5 versus the line at 5. How would I find it? Would you please type in the square root of 5 there for me, please? Let's see how close we are. Square root of 5 is 2.236. Our estimate is 2.25. So what's the error? How would you calculate the error? Take the square root of 5 and then subtract our estimate, which was 2.25 or 2 1/4, and therefore the error is, without respect to sign, it would be negative. Oops, I just shoot. It would be point. Sorry, there's 2.2. 0.1 or 0.01 rather. Excuse me. Yeah. So it's 13 thousandths off. That's pretty stinking good, considering you could do this problem. All right. What if we tried to estimate the square root of 6 with our tangent? Would it be a pretty good estimate? Yes. Why? Graphically. Because they're pretty close. The curve and the line at that are pretty close. Better or worse than our estimate at 5? Yeah, root of x would be good, but worse than root 5 estimate. What about 7? If I went to 7, root 7 would be better estimate or worse? Worse. Okay. The big principle then is the further you get away from the point of tangency, the worse the estimate. Okay. What if you wanted to do the square root of 8? Now, that might seem like a stupid question. I get the trend. It's worse than root 7. But what if you really wanted a good estimate of root 8? Yeah, instead of using 4, instead of using a clean point, a point of tangent at 4, use a closer point, x equals 9. Now, when you do that, students want desperately to manufacture a subtraction in it. They think, oh, I know it's got to be less than, it should be less than our good value of 9, right? And so they try and force the issue of, all right, now I got to take 3 minus this. You don't need to do 3 minus anything. The math takes care of it all because x minus 4, if you tried 8 minus 9, it would be negative. It'll happen on its own. You don't have to force a negative in there to make your estimate less. When you get one that's less, just put the point in like normal, and the sign in here will take care of itself. You'll see in a second. One more side note. Root of x has flat slopes. So less error. If you were to talk about, say you wanted to estimate 2.1 cubed. Actually, let's say something really big. 2.1 to the 5th. No, I don't want to multiply 2.1 times 2.1 times 2.1. That's tedious, okay? I could use a tangent line to estimate that and say, well, I know 2 to the x to the 5th looks like this, and it grows really fast. The thing is with this, if you do 2, then go a little off to 2.1, here's the tangent line at 2, then go off a little to 2.1, there starts to be a really big gap between those two, and that's because x to the 5th grows really fast, the gap gets big fast. It's because this is really flat slope that these are so close to each other. So in terms of how good your estimate is, also depends on what the function is. All right? Let's try one on your own or together. Do you know enough to try one on your own? Not honors people, just regular people. Not that you're not a regular person. You want to try one on your own? Sure. Okay, give it a go. Follow those steps to the side if you're not sure. They should help. I made myself clear. At the end of this, hopefully we'll say a lot of 2 is approximately 20. So your estimate is not yet ready. Right. Your hair hurts? What? I don't know. Okay. It sounds like many of you are just finishing up. We'll give you one more minute. I tend to get excited and go too fast. I don't give you enough time, so I'll wait. Bless you. Okay, let's look at that. Are you ready? So, the point, they say to approximate it with a tangent line of 1. So if the x is 1, then the y is natural log of 1, which is 0. Okay. The derivative. What's the derivative of natural log? 1 over x. Please make sure you labeled your work properly. The derivative at x, then the derivative at 1. The slope at 1 is 1 over 1, so 1. Your tangent line then is y minus 0 equals 1 times x minus 1. In its simplest possible form, I guess we could just say that's y equal x minus 1. That seems to make sense with my picture. Notice the picture, as always, serves to check your work as you're going to say, yeah, that seems right. All right, last but not least, estimate the log of 2. Now, the log of 2 is close to the line at x equal 2. The line at x equal 2 is y equal 2 minus 1, or 1. Your estimate is 1. The natural log of 2 is about 1. The error there is a little greater there because it's pretty steep there. It's a little steeper than the previous example, so we're off. Okay? Questions? Is that an overestimate or an underestimate looking at my picture? Overestimate. Okay. Higher order derivatives. You do higher order derivatives a lot, but let's start with a physics application. If I want to talk change in position with time, that's velocity. How far I went in a time frame. That's velocity. If I did that over a time interval, that's delta x over delta t, change in position over a time interval. But if I wanted at an instant, then I would find the derivative, yeah? X prime, or s prime of t. So, velocity is the derivative of position, right? Right? Right. What if I wanted to talk change in velocity though, over time? How fast is my velocity change? Well, that's change in the change in position. And so that's the derivative of the derivative, which makes it the second derivative. You sometimes want to take a second derivative because you want the change in the change. In terms of notation, if you had an original equation of y, then you might say that derivative notation would be either y prime is common or a Leibniz notation, dy dx. If you are then to write the second derivative, the derivative of that, well, instead of y prime, it's y double prime, or just y double. The Leibniz notation is a little more cumbersome. It is something like this. Pause for a second. That's because taking a derivative is an operation. This could go to improving your understanding of the calculus. So if you had y equals some function over here, just like square rooting both sides, I can square root both sides and it's cool. I could log both sides and it's cool. I could add 2 to both sides and it's cool. I can take the derivative of both sides and it's cool. Now, when you do that, you typically would write that as the derivative of y with respect to x. Whatever you do to one side, you do to the other. Now, in this case, I'm actually then, after that, I'm taking the derivative again. So if I took the derivative again of that, then it would be the derivative of y, or two derivatives over of y, both times with respect to x. That's where that notation comes from. You'll be glad you know it once you get to differential equations. If you use function notation, that's a little easier. The first derivative is f prime, second derivative is f prime. Okay, would you please find the second derivative at 1 of that function below? Try that on your own. Please, careful with notation. That is the biggest source of lost points here. Sorry, I'll get out of your way. Huh? Oh, yes, cool. Thank you. How's it going so far? So this is what I would probably take off. I'd probably take off. They got the right answer, and they would lose 3 points. This, what is it? I have zero idea. You never labeled it. You just wrote some stuff for me. No derivative label, no points. Okay? You will say this is the derivative, and that's y notation. This is the derivative at x. It is 4x plus e to the x plus 1 over x. Okay? This, what is it? I have no idea. Let me just make this clear. The AP rubric was 1 point for first derivative. If you don't have the first derivative labeled, I don't infer for you. That's your job. 0 points. 1 point for the second derivative. Again, if you don't have it labeled, I don't infer for you. 0 points. Okay? Third point, the second derivative at 1. Again, if you don't have it labeled, nothing. I have no idea what you're doing. Yes, you got the right answer. You obviously know something, and you got 0 out of 3 on the AP test. None. You will label, or you will be decimated. Y double is 4 plus e to the x minus x to the negative second. I, in my mind, rewrote this as x to the negative 1. Then, finally, the second derivative specifically at 1 is 4 plus e to the x minus 1, which I suppose you could say is 3 plus e to the, 3 to the 1, e to the 1. So, your final answer is 3 plus e. And you labeled it, yes? Okay, last. Getting back to one of the uses of the second derivative and units. So say I give you the position of a car is 4t squared plus 3t plus 7, where the position is meters from some relative point and time in seconds. If I asked you for the velocity, then velocity is the derivative of position. You could call that s prime or ds dt. Either way, what's the derivative? Yes? 8t plus 3. Now in terms of units, this is so much easier to get the units from this. Change in position is still position units. What are the position units? Meters. Change in time is still time units. What are the time units? Seconds. Okay. Change in position or change in time is meters per second. What about then the acceleration, which is the change in the velocity? So I could, on one level, I could think of that as the first derivative of velocity. But I could also say it's the change in position. So it's the second derivative of acceleration. I could also think of this as dv dt, or the second derivative of position. What is the derivative of 8t plus 3? The derivative of velocity? 8. Okay? What are the units? Now, again, here's the best place to look. dv dt, change in velocity. So the top is velocity units. What are velocity units? Meters per second. The bottom is change in time units, which is seconds. So meters per second per second. You can leave it like that, or you can write it that way. Either one is fine. Acceleration is change in position, or velocity with time. Okay, that's it. So, how do you find the tangent line? You use a point. How do you find the slope? Take the derivative and then put in the point you're interested in. When is a tangent line a good approximator? When you're approximating something near, okay, perfect. Something near to where your tangent line is, or if the curve is flat and slow growing. When is it a bad approximator? When it's something steep or far away. And what's one use for the second derivative? Acceleration. Okay, that's it. Set 26, if you have any questions on that, let me know. I'm thinking maybe a homework quiz or two just to keep you honest, to make sure you're not learning. Or you're not learning. You are learning, excuse me. I've already seen at least one obvious solutions manual kid. But I get them. They typically fail tests right now. So anyway, questions on set 26 if you have any. Let me know. I'll let you get that out.
12, can you look into the square again?
Sure, you bet. 12. If you were, I get the impression that some were hoping in Algebra 1 that completing the square would go away. And gosh, I just use that all the time. Calc 3, Calc 2, all the time. So yeah, that's a skill that I'm glad you're asking about because it's a super important skill. This one's rough in that there's so much going on. Okay, hi. Super. You could just throw it in the basket. Thank you. Okay, so I want to be able to put this in the function mode of my calculator. This is pretty common that you would want to do this. This is not a function, it's a mess. So you're trying to solve for y. Most people, at least I had trouble once I got to this point. I say, okay, I can get the y's together on one side, which I move them over there to be positive, and everything else on the other side, and I'm cool, but then how do I solve for y? Because I have this different power thing. Well, that's why completing the square was created, to deal with that different power thing. We're going to put something there that we can write as a perfect square, and then square root to deal with the power issue. What's the rule for what goes there when you complete the square? Half of the y coefficient squared. So half of 4 is 2, squared is 4. You always balance the equation. So if you add 4 to one side, add 4 to the other. That then would be y plus 2 squared, and on this side, just x squared minus 2x, and the 4's go bye-bye. Now that's wonderful because now you can square root to deal with the square. You can do this next part in one step, but I'll do it in two. If I square root, don't forget plus or minus, so y plus 2 equals plus or minus root x squared minus 2x. So then y is negative 2 plus root x squared minus 2x, or negative 2 minus root x squared minus 2x. And I imagine this is probably a circle, and I just gave top half dollar. Does that make sense? Okay. Other questions on 26? Okay. Let me know if you have any questions. I'll be walking around. If you're shy, I will be happy to help you individually. Make sure I get set 26 by the end of the day. And you do not have the homework. You got to get out of here with your Here's set 27 coming at you. Yes.
So for number 13, when it had a sheet that was 3, but the small scale was 2.5, is it okay to do it with the whole number?
Typically you would do 0.5. Would be my preference. Don't redo it. Yeah, in the future you won't use it. Oh. You okay? Oh, good.
Good morning, Devlin Jaguar. Please rise for the Pledge of Allegiance. Ready? Begin. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Please shout if you have a question.
Ninth graders last name Paige J reports to the auditorium for 7th hour. Ninth graders last name N. Ruthie reports to the cafeteria. Tomorrow, Wednesday, September 6th, 8th graders will be called to the auditorium by Alpha Split after they report to their 10th hour.
If you missed the math testing session, you should report to group E100 at the start of 7th hour today. If you have questions, see assistant principal Coffee.
Show your team spirit by joining us for a fundraiser to support Devlin Boys Golf. Come into the Chipotle at 3170 South Lockwood Boulevard today between 4 p.m. and 8 p.m. Tell the cashier you're supporting the Devlin Boys Golf team. Thank you for your support.
You think science is sweet? Are you mad about math? You love literature? You should sign up to be a peer tutor. Go to the peer tutoring page under academics on the Devlin website to fill out the interest form.
Light Touch will be returning September 12th, starting at 10:20 and running through the end of the school day in the auditorium to get pictures taken for all students or staff that weren't able to get their pictures taken.
Hey students, come join us for the College Day Raffle in the gym on September 6th with some awesome prizes.
All students, mark your planner for Devlin College Day on Wednesday, September 6th. You will have the unique opportunity to meet 14 colleges during lunch in the large gym at 4:30 p.m. to the in-state college fair with 16 Colorado colleges. At 6 p.m. there's a breakout session on various topics. Bring your parents and wear your favorite college t-shirt.
Are you a superstar at science, a magnificent math whiz? If you're a stellar student in any of your classes and you want to help others achieve their best, make sure to fill out the online form to become a peer tutor by tomorrow.
Students, please check the job opportunities board located outside the cafeteria. There are paid and volunteer opportunities available for you.
On Sunday, September 10th at 7 p.m., an information session presented by Brown, Columbia, Cornell, Red, and the University of Chicago will be at the Denver Marriott Tech Center. Must RSVP. Stop by counseling if interested.
Auditions for the talent show will be held this week after school. See Mrs. Shively in the choir room to sign up for an audition time. If after-school times do not work for you, arrangements can be made for a different time. The talent show will be on Friday, September 15th at 7 p.m.
Prayer and Lunch with Students, otherwise known as PALS, is a student prayer group that meets on Wednesdays during both lunches in the conference room of the counseling office. We'd love to have you join us, so bring your lunch and come check us out during lunch tomorrow.
Attention all students, College Day is tomorrow, so please be sure to wear your college shirts. Don't miss out on our college fair and raffle in the main gym during lunch.
Senior high students, seniors, it's that time of year again. You must have all senior pictures and quotes printed by Friday. Email us to yearbook.jags@gmail.com.
And the senior baby pictures cost $50 and are due Friday, September 8th. Email them to yearbook.jags@gmail.com or bring them to Mr. Jacobson's room, L200C in the library. Don't miss out on this fun senior tradition.
Junior high students, the Monday and Wednesday practices at Dublin for the middle school tennis league are now full. Other practices are still available, so it's not too late to join. Flyers are in the main office.
Attention all semis who want to join the Junior High Student Council. The interest meeting will be today. Sign up for your geography teacher and then go to Mr. Teamster. We hope to see you there.
Junior high students and families, the 2017 Dublin Junior High Booster Barbecue Social was a huge achievement. Thank you to those who participated in the evening of food, games, and camaraderie. A big thank you to Scott Fenwell of the Dublin Steering Committee for serving as our grill master. Many thanks to those who helped with cleanup and those who donated food and money to ensure the event's success.
Dazzling Jags. Your cross-country team is lightning fast. Varsity girls earned first place at Lake County with an incredible performance from Corinne Zapico leading the way. The JV girls fought hard for second in their division, and Lucas Jordan was third in the boys' race, rounding out an awesome day at 10,000 plus feet.
Jags, come support the cheer team at the Panera on 650 South Waterford Boulevard today from 4 to 8 p.m. before the soccer game at 7. Be sure to mention Dylan and see you there. Today, your sporting events are softball at Arapahoe High School at 4 o'clock, volleyball at Elizabeth High School at 6:30, and soccer versus Dakota Ridge at Lakewood Memorial Field at 7. The theme is ski bump.
Before I end announcements today, I have to say I absolutely